Take a standard bar magnet. It has a clearly defined north pole on one end and a south pole on the other. What happens if you try to snap it in half to keep the north pole all to yourself? You don't end up with an isolated north and an isolated south. The material instantly reorganizes to form two brand new, smaller magnets, each with its own north and south pole. This is a strict limitation of magnetism, and it contrasts sharply with how electricity works. We can easily isolate a single positive or negative electric charge. You can hold a solitary electron. Maxwell's equations describe electricity and magnetism as a single symmetric system, yet in our hands they behave with this glaring asymmetry. We are hunting for a particle that the math suggests should exist, but the material world refuses to provide. In the 19th century, James Clerk Maxwell codified this physical barrier into a mathematical rule known as Gauss's law for magnetism. The law states that magnetic fields have zero bivertence. This means their field lines cannot begin or end on a point. They must flow in continuous, unbroken loops from north to south and back through the material. You cannot separate a loop's beginning from its end. When you cut the magnet, the field lines instantly pinch off, forcing the creation of two smaller, self-contained loops. This geometry governs everything from refrigerator magnets to the Earth itself, which behaves as if a giant, unbreakable dipole is locked in its core. In classical physics, separating a north and south pole isn't a matter of applying enough mechanical force. It is an impossibility dictated by the geometry of space. By 1931, physicist Paul Dirac looked at the equations of electromagnetism and found this lack of symmetry aggravating. Dirac proved that under the laws of quantum mechanics, a single isolated magnetic pole, a magnetic monopole, actually can exist, but it requires a specific condition. The monopole must connect to a Dirac string, an infinitely thin topological defect feeding the magnetic field into the particle. Consequently, if a single magnetic monopole exists anywhere, it mathematically demands that all electric charge must be quantized into discrete, uniform packets. Since every electron in every atom carries this precise, uniform charge, the monopole serves as the mathematical anchor that keeps the material universe consistent. Theoretical physics suggests these monopoles were forged in the first trillionth of a second after the Big Bang, in temperatures exceeding 10 nonillion degrees Kelvin. For decades, scientists have scoured the Earth for these primordial particles, dragging magnetometers over polar volcanic rocks and analyzing soil samples returned from the Moon. They have built massive detectors at particle colliders, like the Moadal experiment at CERN, attempting to forge a magnetic charge from scratch by recreating the intense energy of the early universe. After a century of smashing atoms and sifting through cosmic dust, natural magnetic monopoles remain completely absent. If we want to study an isolated pole, we have to build an environment that forces it to exist. To bypass the limits of classical magnets, physicists turned to engineered materials. They grew crystals known as spin ices, such as dysprosium titanate. These materials consist of a geometrically frustrated lattice composed of pyramid-shaped tetrahedrons. Inside this crystal structure, the atomic magnetic spins are forced to obey strict ice rules to maintain stability. On any given pyramid, exactly 2 spins must point inward, and 2 must point outward. This 2-in, 2-out balance cancels out any net magnetic charge across the material. It perfectly mimics the unbreakable closed-loop behavior of a standard bar magnet. But if you inject enough thermal energy into this crystal, you can forcefully flip a single atomic spin against the rules. Suddenly, that pyramid has 3 spins pointing in and only 1 out, creating a net magnetic charge, an isolated pole. This forged charge then wanders through the crystal, leaving a jagged trail of flip spins behind it, a physical Dirac string. You cannot mechanically separate the poles of a standard magnet because the geometry of our macroscopic world is built out of closed loops. But by engineering new phases of matter from the atoms up, we have finally learned how to untie those loops and let the poles roam free.